So as I told you, I am going to talk about the devil point, and well, this is what we call a critical point, and it's going to be, I guess, hopefully very exciting. So I will probably spend much of my time for the introduction, and of course, if I will have some time at the end, I will discuss about this boundary layer instability. So I will first introduce the supercritical fluid. What is a supercritical fluid? So we are going to talk about the near critical point, and then I will discuss about the thermal vibrational instabilities in supercritical fluid. The temperature below, this is something which we were not able to understand, so we have understood this at the end. Some experimental results, I don't know if Khatul is here, but he was interested in this. I guess he might have disappeared. And then perspectives and conclusion. So just to begin with, there are plenty of plenty of applications. I will just give you two basic applications which relates to near critical fluids. I will come back to this diagram before. So this is during regenerative cooling of engine, operating conditions closer to the critical point. Well, I don't want to go in the numbers right now. And when we have mixed of oxygen during combustion, local mixture conditions are also closer to the critical point. So in the cooling process, you have also some parts of the process which is in the near critical conditions. There is another example, which is the power generation. The power generation, well, the basic idea is that you can see here in this diagram, which is not very clear, but sorry about this. So you have the critical point here, and you have all the process which is going to go to the compression, expansion, and cooling, and so on, is done under supercritical conditions. So the efficiency, as you can see here, the efficiency is becoming higher. I don't want to go too much into details about this. So you have also plenty of applications in the soil. You know, if you go in the soil, deep in the soil, the conditions are absolutely supercritical. So this is some of the challenges. Okay, so introduction. So I guess as this is much more for PhD students, I will go very, very slowly on that. So what is a critical point? I guess you might all know about this. So I'm not talking about what Jean-Pierre was talking this morning. He is talking about a critical point, which is liquid critical point. I am much more talking about liquid vapor critical point. Well, both of them are complex. And as I told you, this is a devil point because I will go through it later on. So this is the phase diagram, and you have liquid, gas, and so this is the two-phase system. And so as soon as you go nearby the critical point, something strange is happening. So I will go through it. Okay, so this is the two-phase, I mean, pressure, volume, and you have a pressure temperature. So I will probably much more focus on this pressure volume. So this is, of course, the coexistence curve, which is the liquid vapor coexistence curve. So this is delta rho, and I am supposed to have some animation. I'm not sure it's going to work. Well, anyway, so what I wanted to show is that as soon as you go more and more to the critical point, this delta rho, which is the density variation, is going to zero. Well, this is the first thing to say here. The rest is going to come later on. Critical opalescence, I guess somebody has talked to this about this in the morning, probably. So the critical opalescence is that when you have a two-phase system, you increase the temperature of the system. So you have a two-phase here, so this is going to be some kind of mixing. And then you have, I guess it's Jean-Pierre who has talked about this, you have a milky process which is related to light. So this is a supercritical state. Okay, so a fluid is considered to be a liquid and a gas, or a gas. But supercritical fluids, it's at the same time a liquid and at the same time a gas. So this is very strange. So liquid has a high density. Gas, of course, has a low viscosity and high compressibility, and supercritical is both of them. So this is the first problem which is right now, which we are facing right now. Okay, how is the behavior of the various properties are going to be affected. So we will go to this slowly here. So all these various properties have some kind of relationship which is written here. So you have a regular part, and you have here something which is dependent on epsilon. So you need to really put this in your mind regarding epsilon, definition of epsilon. So T minus Tc. Tc is the critical temperature, and so this is an important parameter for us. As I told you here, so this is the regular part, and this is the something like singular part of a property, and I will come back to this later on. So as epsilon is going to 0, so the density fluctuations are going to infinity. So this is going to govern the whole behavior, and so you will need something like a universal behavior, which is the critical universality. Okay, so as I was telling you at the beginning, critical contributions distinguishable from mean contributions. So fluid term as near critical fluid. So sometimes we just get rid of this one because this one is either extremely high or extremely low. So how are the near critical fluids different? When approaching the critical point, you have diverging properties. So I will go back to this one later on. This is isothermal compressibility, thermal expansion coefficient, heat capacity at constant volume and constant pressure. But you will see that there is some differences. I will come back to this. You have also something very strange here, is that some of the properties are vanishing, or of course we call this tending to 0. So speed of sound and thermal diffusivity are both going to 0. Okay, so it's a really system which is completely strange, and there is another point here. I will come back to this later on. Heat transfer is governed primarily what we call piston effect, and I will come back to this in details later on. Okay, so I don't want to go to the whole properties, but I will just give you 2 examples. So you have all the properties here. Okay. So the definition of the properties here, well, some of the properties, and so the behavior. So this is, as I told you, the epsilon, and this is what we call the critical exponent. For example, if you look at the isothermal compressibility, the critical exponent is 1.2, so it diverges very, 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 very fast. But if you look at the speed of sound, for example, because people are telling me that, okay, it's going to be highly compressible, what is your Mach number and so on. But speed of sound has a critical exponent which is 0.11, 11 divided by 2, so it's 0.05. So it's extremely small, so the speed of sound is almost constant. Okay, so I will not go to all the properties, but I'm just giving you 2 examples in order to see that why I'm calling this a devil point, because everything is either diverging or going to. Okay, so there are some other properties. I will go a little bit faster here. Of course, everybody knows about the Mayer relation, which gives the difference between the heat capacities. But you know, in this part, as I told you, compressibility is going to infinity. So what is going to behave the CP, for example, the heat capacity at the constant pressure? This guy is constant. As soon as you put a small temperature perturbation, the pressure is not changing, but the density is changing almost exponentially. So this guy is going to go extremely fast to the critical point. I mean, it's going to diverge. So this is, I guess, what I was telling you here. So CP, beta P, which is the thermal expansion coefficient, gamma, which is the specific heat ratio, are all going to infinity. Okay, the speed of sound, as I told you, it's the same behavior, almost the same behavior as 1 over square root of CV, which is the heat capacity at constant volume. So speed of sound, as I told you, going to 0, but extremely slowly. Okay, so shear viscosity is almost, again, constant, exactly the same behavior as the speed of sound. You can interrupt me if you have any questions, because everything is a little bit diverging here. So thermal conductivity is also going to infinity with a critical exponent which is not too small. So thermal conductivity is going to 0. But you are going to say, yeah, thermal conductivity is going to 0. So thermal diffusivity, it's lambda over Cp. But lambda over Cp has a critical exponent which is higher than lambda. So the thermal diffusivity is going to 0. Okay, so this will have some effect of the piston effect, which I am going to talk. Okay, I put this in red because this is a long debate regarding the bulk viscosity. And I guess probably Stéphane and Jacques know about this. Yeah, I guess you know about this because... Yeah, probably. So there is has been shown by Kadanoff a long time back. Well, the critical exponent is extremely high, it's almost 2. So, but nobody is taking into account because it's extremely probably valid, I would say. Extremely probably valid, I'm not sure about this. Very, very, very close to the critical point. And Pierre Carles has also written something on that, and he thinks also that Pierre Carles, who is a researcher in Paris, so he has also proven that bulk viscosity have some effects extremely near the critical point. You can give your opinion on that if you want, like right now, but so let's continue. So supercritical fluid is dense as a liquid, so this is the conclusion. It's dense as a liquid, compressible, and extremely compressible, and very viscous like a gas. So it's a particular system in a hydrodynamic point of view. So this is why I was interested. As soon as there is something singular, I'm extremely interested in. So yeah, okay. How about the piston effect? I'm still in the introduction part. So piston, well, it's almost, yeah. Well, the viscosity is almost the same as a gas. Okay, it's the same.
So it's low viscosity.
Yeah, exactly. Right. So this means that yeah, usually you have a liquid. This is what I'm saying. The only thing is that it's at the same time liquid and gas. So this is what I'm saying. In a hydrodynamic point of view, it's a very particular system. So this piston effect, I'm just giving you a story about this, about the piston effect. This was something, I guess, Straub in 85. He was doing some experiment in a parabolic effect. So he found something very strange nearby the critical point. So I don't want to go into details about what he found. And so some researchers around the world, 3 teams, independent teams, completely independent teams, have proven what was the reason. So the basic reason, I will give it to you. So one is, I guess, Onuki in Japan, Bukhari in US, and Zapoli in France. So they have all proven by analytical solutions, by thermodynamic point of view, and so on. So what is the problem? So if imagine you have a container and you hit the left boundary, okay? Thermal diffusivity is going to 0. So heat should not propagate. But what we have found, I mean what Straub has found also in his experiment, is that it's almost propagating at the speed of sound. So what was the reason? Of course, because it's highly compressible, so you have waves which are propagating with lots of energy. So the propagation of the waves thermalize the system almost at the speed of sound. So this is the main point which has been, it's about the years of 90s. So this is, I'm just giving you some profile here. I do not see it here. So delta T as a function of X. So this is for a perfect gas. Just a comparison, just give you an idea. And this is for a near critical fluids. As you can see, is that it homogenizes almost at the speed of sound. Well, homogenizes almost at the speed of sound. So I guess I'm not going too much into details, but I have a simple approach, which has been well, I have discussed this with Daniel Bessin, Yves Garabos, and Bernard Zapoli. So this is our conclusion. For a simple analysis, is that this is what's called simplified model. So you have internal energy at the thermal boundary layer, So it's, of course, this is delta is your thermal boundary layer, yeah, because the thermal boundary layer is extremely, extremely small. because the thermal diffusivity is going to 0. So this is what we have in the boundary layer. And so in the bulk, so it's of course at constant volume. So this is at constant pressure and constant volume. Of course, the bulk is the L length. And so our goal is to see what is going to be the time. Sorry, yeah, please. Well, you are talking about in a small scale. Huh? I'm talking about macro scale. Is that you have the definition of dt is lambda over rho Cp. Okay, lambda has a critical exponent of 0.5. And Cp has a critical exponent of 1. Yeah, the fluctuation, of course, it's thermal fluctuations. Yeah, you are right. So it's in a molecular point of view, I guess it's of course it's thermal. This is what you are probably also have the same answer. So you have extremely high fluctuations of density. Okay, I guess you. Okay.
So does it matter how slowly or quickly you heat this air? You want to do it very, very slowly. You still would have a wave that propagates.
Yes, yes. You all the time, as soon as you have a thermal perturbation, you will have propagation of waves. And the waves are having lots of energy because of compressibility, which is going to infinity. But you have three terms. Compressibility, thermal expansion at the same time, and heat capacity at constant pressure. These three are diverging with the same critical exponent. So of course, the propagation of acoustic waves, it's lots of energy, and it's, I guess, I don't have this here, but Pierre Carles with asymptotic analysis, he has proven very nicely that when you go from the momentum equations to the energy equations, the large term is coming from this P grad V, P divergence of V. And this is huge, acoustic waves here. But acoustic waves, but in a compressible case, you will have small energy, but in a highly compressible, like what we are treating, it's lots of energy. Okay, so our goal is to see, yeah, please.
It will get accounted for automatically. The thermal conductivity will be, diffusivity will be very low, but then the convective part, because of high speed, will take care of the fast convection. It's there in the equations.
Exactly. You are talking about non-isothermal system? No, non-isothermal system. Of course, well, it's a good question. But you are talking about non-isothermal systems. You are talking about at the same time conductivity. I don't understand. Yeah, but you are saying you are talking about non-isothermal system, right? This is sorry. Yeah. Okay. So the question is, as soon as you hit the left boundary, everything is adiabatic. When you hit the left boundary here, so heat will not propagate because the diffusivity is 0. But because of, as I was telling you here, is that because you have propagation of acoustic waves back and forth, which is with the speed of sound, which is almost 300, for example, if we take for air. So in that case, you will have the thermalization almost at the speed of sound. It is supposed to not propagate, but I guess it's propagating because of loss of energy of acoustic waves. But this is for the energy equation, you have dt over dt. So this the asymptotic analysis, as I told you, I had some slides, but I don't have it right now. But we can discuss about this later. But it's a good question because there is a transfer of the momentum from what you have in the momentum equations. It's going through this energy through this pressure term, because in the energy equations it's if I remember quite well, it's beta T dp over dt. So as soon as you have exactly, yeah, totally. But I guess I should have put this because it's a very important question. So this is a very simple model. I just want to show you what's going to happen, because the goal is to say, okay, what is going to be when the thermalization of the system, which means that this temperature is going to be equal to this one. What's going to happen? Okay, so as I told you, we are trying to see what is going to be when these two temperatures are equal. So of course the same energy. Well, we cannot put energy elsewhere, so it's the same energy. So in that case, we are going to calculate this delta from the classical relationship. So this is what we call extremely important. This is the piston effect timescale. So the piston effect timescale, it's d, which is the diffusion timescale, over gamma, as I told you before, gamma is going to infinity at the critical point. So gamma going to infinity at the critical point, and TD is going to infinity at the same time at the critical point. Sorry, it's a CP over CV. It's not surface tension. It's CP over CV. Yeah, I know that the notation is okay. So this means that TD is going to infinity, but you will see later on is that this piston effect timescale is going to zero at the. Will probably give you. Well, these are all the characteristic timescales. So you have acoustic timescale, which is the classical acoustic timescale. This is the new timescale which we have, which goes to zero as a critical exponent, which is extremely high. Viscous, as I told you, is constant, even if it is diverging slowly. But I don't talk about bulk viscosity. So, and then you have the thermal diffusion timescale, which goes to infinity with a power which is not too small. Okay, just to give you an idea, we have done some basic calculations. So this is a CO2, 20 centimeter of cell. We are extremely close to the critical point, and here we are extremely far from the critical point. This is the order of magnitude of all timescales. Piston effect timescales, 4 seconds. When you are going far away from the critical point, 6 days. But look at this here also at the same time. Thermal diffusion timescale, 20 years and 8 days for when you are far from the critical point. So this is just to give you an idea about the relationship between different timescales like piston effect timescales and diffusion time. Well, viscous is the same as I told you because it's a constant. Okay, right now, so this is the first part of the devil point. The second part of the devil point, well, all dimensionless numbers are either going to infinity, well, most of them are going to infinity. Just to continue on that, so you have, I guess I will probably, it's better to explain you very clearly about what is happening near critical point, because if I don't have time, it's okay, I will not go to the thermal boundary instabilities. So what we have here is that, for example, Prandtl number, Bond number, Rayleigh number are all diverging at the critical point. So of course the system is becoming more and more unstable. You are going to put a very small temperature perturbation, it's going to be unstable almost instantaneously. Sorry. Okay, so well, I already said about compressibility. So compression under self-weight. So you have also, this is also a very good point. You have strong density stratification. And this is what I'm going to talk, I guess it's the next one. Yeah. So, I discussed with, I don't remember his name. He has left today. He was talking about Kolmogorov scale in turbulence. So he was studying about Rayleigh of 10 to the 13. So I told him that my Rayleigh is divergent. So it's very interesting. Well, so Rayleigh-Bénard convection, just to give you an idea, is that when you have atmospheric layers, so it's some kilometers, you can do the same experiment in millimeter cells, in near critical fluids. So this is okay, so the Rayleigh-Bénard configuration, of course, everybody knows that. So you hit the lower cell. And so the delta T onset, the delta temperature onset, it's dependent on two parts. So the first part is asymptotically going to zero near the critical point because of the divergence of this guy and this guy at the same time. Even if this guy is diverging. But the multiplication beta by CP is diverging more than lambda. And the second one, which is not very well known for probably most of my students when I'm talking about this, is the Schwarzschild criteria. I guess probably you know about this. It's independent of the critical point because beta and CP are diverging with the same critical exponent. So it's a constant. Okay. So yeah, as I told you. So if you plot, well, I'm just going to give you an idea. If you plot delta T onset as a function of epsilon, so this is what you obtain. So this is the part of Schwarzschild, and this is a part of classical Rayleigh when you are going very far from the critical point. So the overall idea is to say that when you have fluids near the critical point. Far from the critical point, you have classical Rayleigh number, as I told you here. And near the critical point, you have Schwarzschild criteria, which you can find only in atmospheric layers. And for perfect gas, of course, when L is large, as I was telling you, atmospheric layers, Schwarzschild criteria, and when L is small, Rayleigh criteria. The mathematical formulation is extremely easy. So I don't want to go too much into detail, but of course, you all know all these equations. And what we have done, well, you have this equation of state, which is the key point. I guess many people are showing this with a very complex real equation of state. But I guess while with the model of van der Waals, everything you can do it is very, very nice. But if you want to compare, of course, with experiments, it's not easy. So what we did, I will just go a little bit faster here because I have only 5 minutes. So what we did here, something very, this has been done by my colleague Jean-Pierre Caltagirone. So what we did here is the pressure, of course, it's a classical way to do it, and we express this derivative of pressure as a function of time, as a function of compressibility and thermal expansion coefficient, beta. So we have this dP over dt because this is the key point, because the problem is that, I will come back a little bit earlier here. It was not here, sorry. Let me go to what I wanted to tell you here. Okay, so from this, we have submitted to this to International Journal of Multi-Phase Flow, and some reviewers were saying that, okay, your hypothesis is not valid because we are integrating here as a function of time. So, but we told, okay, this is delta t, which is our time step. So it's a hypothesis. In our time step, this is constant. This is constant. Okay, so this is a p, and I will just go very fast here. So these are our modified equations here. So this is all the red term, this is what we are doing right now. And if you have some questions later on, because I don't want to go too much of the details on that, I will show you at least some results. Okay, so what is this here? So of course you have to adapt from what you have done before. All properties, either you can go for NIST, and for me, as I told you, van der Waals is sufficient. Renormalization, group theory, Ising model, whatever you want. So the only thing is that what we have here is there is no unknown pressure present in the momentum equation. This is for the numerical solutions. So this circumvents the need of any pressure-velocity coupling, I just presented to you before. So Rho is calculated directly from the continuity equations and permits higher temperature perturbations. Well, so this is the numerical solution, and I don't want to go too much into details because this is the code from the lab, and this has been done by one PhD student, which I'm going to present right now. So I will go for the results. Okay, the results, I will just go to some of the results, previous results. It's old results, so old 2016. So there was an experiment from the team of Daniel Bessens. He's doing a very nice experiment. And he has done a quenching. So quenching from Tc3 plus 3 millikelvin to Tc plus 2 millikelvin. And he has a cylindrical cell filled with supercritical fluid. Okay, and so he quenches all the walls here. Of course, the walls for the cylinder, for the sphere, sorry. And then he finds some kind of instability. So he wanted to understand, and of course we have collaborated on that in a numerical point of view. So we have done the same, and we have found almost, it was a square cavity, because I didn't want to go to some kind of a sphere cavity. So square cavity, we are obtaining almost the same kind of things. And so this is vibration like this, and this is vibration like this. So this is what we call parametric instability. The first one has been done by Diwakar Sharma. Of course, my Indian collaboration is very active, so there are many Indians also, and there is also another Indian, Gurunath Kandikata. I guess he's now working in a company in India, in Bangalore. So we have shown that, okay, this instability exists. And there is also a very nice work from Shestova. The team has shown that you have instabilities in this direction and in the other direction. So both of these instabilities have been covered. So they have also shown this very recently. I guess I have 2 minutes, right? If you are the chief, I will agree. Okay, so what we have, well, this is the thesis from Divakar Sharma. Simultaneous thermal perturbation and vibration in the zero condition. So this is what we have done, exactly the same case as experiment. So what I need to follow here is that relay vibration instability is that when vibration is perpendicular to the temperature gradient. This is what we call relay vibration instability. So he has done a nice job regarding this. So this cavity is filled with near critical fluids. You vibrate horizontally, and you have these walls are adiabatic, and you are quenching, or either you are quenching or you are putting this adiabatic. So I'm just giving you, and so this is relay vibration instability, and parametric instability is vibration is parallel to the temperature. Well, one of the parametric instability is Faraday instability, and we have done this also at the same time. Yeah, so this is just to show you the results regarding the comparison with experiment. So he has done also a very good job, and well, this is I would say matching quite well, but I will not talk about this right now. Yeah, okay. So why do we have a thermal vibrational instability? So delta TBL, thermal boundary layer. So this is, of course, thickness of the thermal boundary layer. When it increases, difference in inertia force and thus delta P increases, overcomes the stabilization action, and TBL becomes unstable. So it's a very simple sketch in order not to go to the modeling part. I will just finish this with that, if you permit. Okay, just one slide regarding this is very well known in a very excellent book from Gershoni and Lyubimov, thermal vibrational convection. So they have done a very nice configuration. Of course, it's almost Rayleigh-Benard configuration, but of course you have vibration at the same time. So this is the definition of the Rayleigh vibrational. So A is amplitude of the vibration, omega is the frequency. So of course, I have not shown here, but this Rayleigh vibrational is also going to infinity. Again, another problem. So, but E, in this case, E is replaced by the thermal boundary layer thickness. Okay, so this is the general idea.
Long live India and France friendship.